within his general theory of relativity. Gravitational waves arise when heavy bodies accelerate, that is, when their velocity is changing with time. They are disturbances of space-time traveling through the universe at the speed of light, causing space to alternately stretch and shrink at right angles to the direction of motion. Now, the effect, the gravitational strain, is tiny, even from a ponderous event like the collision and merger of two black holes. If we imagine a ruler, the length of the Earth's diameter, like 13,000 kilometers, a passing gravitational wave would make this ruler vibrate by 1/1,000,000th of a millimeter, which is about the size of an atomic nucleus. Nevertheless, the team of scientists led by this year's Nobel laureate succeeded in measuring this tiny vibrance. The key to this success is laser interferometry. And I'm now trying to explain the principle behind laser interferometry for you. The light from a laser is led towards a beam splitter where the light is split along two detector arms at right angle to each other. In the case of LIGO, these detector arms are 4 kilometers long. Mirrors at the end of the arms reflect the light back towards the beam splitter, where the two waves are overlaid and channeled towards the light detector, where a fringe pattern is registered. Now, a passing gravitational wave will make one of the arms shrink when the other arm expands, and this makes the pattern shift very, very slightly. And this is what the scientists detect. Now, the effect is incredibly small, and the detector is amazingly sensitive. A passing truck or ocean waves beating against a far shore cause a disturbance, which must be monitored and offset. Also, to exclude local disturbances, each LIGO detector cannot operate on its own. And this is why the LIGO Observatory comprises two detectors, one in Hanford in Washington State and the other in Livingston, Louisiana, on opposite coasts of the American continent, separated by about 3,000 kilometers. And on the left hand, you see panels showing you the gravitational wave registered on September 14, 2015 by the two detectors. The upper panel shows the wave registered at Hanford, the middle panel at Livingston, and the bottom panel shows the two waveforms overlaid, shifted by the time difference between the gravitational wave's arrival at the two sides, which was 6.9 milliseconds. And what I would like you to note in the bottom panel is how identical the two waveforms are. And this is essential to be able to recognize this event as a true occurrence and not a false signal. Now, looking at this lower hand, at the left-hand panel, I would like you to know something else, namely that the waveforms wiggle faster and faster as time progresses to reach a climax at about 0.4 seconds. This is the point when the black holes merge, and then to quiet down signal. And I'm going to play for you this audible signal, the now so famous chirp of the gravitational wave. But to do that, you have to be very quiet and listen for a faint twang, which is when the two black holes merge. I'm going to play this 4 times. So here goes. And this brings me to my last slide. The discovery, the first ever observation of a gravitational wave, was a milestone, opening a new window to the universe. the prospects of observing black holes hands-on are tremendously exciting, as are the prospects of being able to see the dark parts of the universe, the parts of the universe from which electromagnetic radiation, light, does not reach us. Since the first observation, 3 more discoveries of gravitational waves passing the Earth have been made. The last one announced less than a week ago, where the twin LIGO detectors operated in concert with their sister detector Virgo in Italy. This is truly the dawn of gravitational wave astronomy. And I couldn't help but end with Einstein, who obviously was right again, even though back when, for a while, he didn't believe that gravitational waves existed. And so I'm going to leave you with a picture of the 3 Nobel laureates, the leaders of the international team of scientists behind the discovery that shook the world. Thank you.
Thank you very much, Olga, for that exciting introduction to the field. And we may now have one of our Nobel laureates with us on a phone line from the US. Dr. Weiss, are you there?
Oh, I'm here, yes. Can you hear me?
Yes, absolutely. Good morning. This is Göran Hansen, the guy who woke you up
Okay.
an hour ago or so. How are you now?
I'm fine. I even have clothing on. Yeah.
Very good. It's just a phone line, so it's not absolutely
That's
mandatory,
fine.
but you don't have to freeze then. So I'm now sitting in the beautiful session hall of the Royal Swedish Academy of Sciences. We're in the midst of the press conference. Here are journalists from Swedish and international media, and I'm sure they would like to ask you some questions. So are you ready for them, Dr. Weiss?
I hope I am. I hope I can understand.
Yeah. Please, Thomas von Heine.
Good morning, Professor. Congratulations. Swedish television. Von Heine is my name. I'm curious. We just heard that now by sort of seeing these gravitational waves, you can deduce what happened when 2 black holes merged. And what else is there that we can learn now that we can detect them?
Well, there's a huge amount of things to find out in the universe that radiate gravitational waves. I mean, the black holes are probably the strongest source, but there are many, many others. And for example, the neutron stars themselves, which are now stars that are not yet black holes, they are still stars that are quite finite in size. When they get together, in fact, the very first discovery that was made of gravitational waves, indirect discovery, but a very important one, was done with a pair of neutron stars. There was a Nobel Prize given for that back in the 90s, where they were observed, neutron stars, they're in a pair, kept going around each other. And through the motions, you could determine the motions of the 2 stars. You could determine that they were radiating gravitational waves. It was a major discovery in the field of gravitation. The other kinds of things that was we hope to see those. We hope to see, in fact, the supernova at one point. It's not so easy. There are not so many of them, but these are stars that have come to the end of their lives, and they then rapidly collapse. And in the process of collapsing, if they have any kind of a spherical motion that is completely spherical, which most likely will be the case, they will also radiate. And in fact, they will radiate and tell us really what goes on in the supernova, which would be absolutely fascinating. Then there is in the future also the business, eventually the idea of looking for a background radiation of gravitational waves, which is just a noise that comes from the whole universe in a way, because you have quite resolved all the sources. But there will be a background noise of gravitational waves. So there is now way of looking, technique that was developed, of looking at a part of the universe never really seen before. A lot of things that do not send their messages out electromagnetically. They send them out by making gravitational waves. So we're very hopeful that becomes really part of astronomy and astrophysics, not just the uniqueness of having made a detection of single gravitational waves for a few of them. This becomes part of the science of understanding the universe.
Okay, thank you very much. There's a slight problem with the phone line, but I think you could hear. We have a question over there.
Yeah.
Congratulations, Professor Weiss. I'm Sufficient Access Song, freelance reporter for China Radio and also reporter for Green Post. My question is, did you expect this, or did you know that you have been nominated? And what was your reaction when you heard the news? Thank you.
Right. Yeah, it's really wonderful. I mean, I view this more as a thing that it recognizes the work of about 1,000 people, and it's the work, really a dedicated effort that has been going on for, I hate to tell you, it's as long as 40 years of people thinking about this, trying to make a detection of, sometimes failing in the early days, and then slowly but surely getting the technology together to be able to do it. And it's very, very exciting that it worked out in the end, that we are actually detecting things and actually adding to the knowledge through gravitational waves of what goes on in the universe. It's a wonderful experience, sort of begun anew. And many of us who are in this thing fully expect that we're going to learn things that we didn't know about. I mean, at this moment, we knew about black holes other ways, and we knew about neutron stars. We've known about, well, those are the two things that ultimately are seen. But the thing is that we hope that there are all sorts of phenomena that you can see mostly because of the gravitational waves they emit. That will open a new science and will add to the science that is already, such a deep thing in terms of understanding the universe. So I can't answer you any better than that.
I think that was a great answer. Thank you very much. More questions? The lady over there.
Hi, I'm Annelie Megner Arn, and I'm from the Swedish TV4. Congratulations, this was a really cool discovery. I wonder when Röntgen got the first Nobel Prize in physics, when he discovered the X-ray, I don't think he thought that in 100 or a little bit more time we would be using these X-ray waves in hospitals daily and dentists and so on. And I wonder...
Improving sensitivity so that we can look deeper and deeper into the universe. And in particular, we hope at some point, but not the detectors we have now, because they're not strong enough, they're not sensitive enough. We hope to be able to look at the beginnings of the universe. For example, we hope at some point to have detectors that are sensitive enough so that you can spot black holes over the entire universe, so that you can see the evolution of that particular kind of source. And as time goes on, we hope the detectors get more and more sensitive. But I don't think they'll get necessarily smaller. Yeah, that's my guess. They will probably get more and more sensitive if we do our job properly. People who follow us learn how to make the detector better. There's easily another factor behind that in the sensitivity of these detectors. And in the process, one would imagine that you begin things like the very earliest moments in the universe. It's one of the ideas I've thought about a lot. But detectors are not sensitive enough to see that. For example, there are calculations that have been done that indicate that the very earliest instance of the universe, right after the universe gets born, there is an enormous amount of background radiation of gravitational waves generated. And that would be absolutely fascinating to see. Now, there are methods that are being tried right now to see those by using radio astronomy and looking at effects that occur later on in the universe as driven by the earliest gravitational waves. I hope those, but there may yet be need to do this very directly, to look at the gravitational waves directly that come from that earliest effort. That would be one of the most fascinating things man could do, because it'll tell you very much how the universe started. The fascinating idea in gravitational waves, since they're so imperturbable, they go through everything. They will tell you most information that you get about the earliest infants that go on in the universe. At least I hope so. You know, I think it's an opening field. It's a wonderful field, and I hope it's with man until we really get everything to the point where the sensitivities are such that we can do cosmological investigation using gravitational.
Okay, we're running a bit short of time. I think there is time for one short question, one short answer, please.
Yes.
Good morning, Professor Weiss. My name is Erika Neckham. I'm working at the Swedish National News Agency, TT. Congratulations at first. I would like to know what you felt like when you heard the gravitational wave for the first time.
Well, when we first discovered them, back in September of 2015, rather, many of us didn't believe it. I have to tell you that. We have a program where we inject signals to test the detector. That's what we thought I was seeing. It took us a long time, almost something like 2 months, to really convince ourselves that we had seen a thing that came from the outside and was truly a gravitational wave. It was not trivial to convince oneself that one had seen those. And then, as time has now gone on, we've seen more of these events, similar kinds of events from black holes, and it makes it more and more likely, and I'm now very much convinced, I don't think there's anybody left, doubts that detected these gravitational waves.
Okay. Thank you very much, Professor Weiss, for being with us at this press conference, and we're looking forward to welcoming you to Stockholm in December. Thank you very much.
I look forward to it too. Thank you. Bye-bye.
Bye. And now, are there any questions for the panel? Or Dr. Botner and Dr. Weiss explained it all to you? Okay, in that case, if there are no further questions, we'll close this session, and I know that several of you have requested individual interviews that will commence. So, thank you very much.
The amazing thing is that no humans existed when black holes collided, but while the waves traveled through the universe, Homo sapiens developed on Earth, and by the time the waves reached the Earth, we not only existed, but had developed instruments which were sufficiently sensitive to detect this tiny, tiny vibration of Earth when the gravitational wave swept past.
Where was it? Where was the collision?
Oh, the collision was 400 megaparsec away. We don't know which galaxy it was exactly, but we know that it was 1.3 billion light years away, which is quite far away. But it's very difficult to pinpoint the location exactly because the detectors we have are not very sensitive directionally. So they can point to an arc on the sky where it might have happened, but cannot say exactly that this was where it was.
Could it happen closer to us?
It could happen closer to us. It might happen closer to us in the near future, but we're getting so few gravitational waves at this time that I cannot tell you when we'll see something which is even closer.
Would this be dangerous for us on the Earth?
This will probably not be dangerous for us unless Earth would collide with a black hole, which is not going to happen anytime soon. But the effect is so tremendously small. And here we're talking about trillionths of a millimeter on a length which is the size of the diameter of the Earth. That this is not something which an ordinary human would even feel. This is why we need these extremely sensitive instruments.
So even when they arrived at Earth, nobody could feel it.
That's right.
Although they went just through us.
So we believe that there are gravitational waves sweeping through the Earth all the time. Now even now. And if we're lucky and the amplitude is slightly larger, then we are able to detect them. But mostly we are not even able to see them.
What was this sound of the gravitational wave, like?
Oh, so the point is, and I want to stress that gravitational waves are not sound. But the waveform has wiggles in them. And if you look at these wiggles and how they vary over time, you can represent what you see in terms of an audible signal. And this was the chirp we just heard. So it so happens that the frequency of these waveforms is almost the range of human hearing. And this is why we're saying that the gravitational waves are loud, that we can hear them.
So what was the main achievement of this year's laureates?
So their competencies are quite complementary. Rainer Weiss is the founder of the whole project. He developed the concept starting in the beginning or the middle of the 1960s. He built the first prototype detectors in 1967, and then he demonstrated the principle. He charted the various noise sources which would influence the performance of the detector. And as I've been trying to mention, the detector is incredibly sensitive. A truck passing by will make the detector vibrate. Ocean waves some distance away make also the detector vibrate, seismology, other things. So you have to know very, very well what kind of sources can give you signals which simulate gravitational wave to be able to distinguish the true from the false. So his main influence on the project is developing a prototype, charting all the sources of disturbances, and finding means to offset these sources. Thorne is this inspiring theorist who figured out what kind of signals you can expect from astrophysical sources of these waves. So what to look for, how sensitive does the instrument have to be able to observe what the universe behaves like in terms of gravitational waves. And then we have Barry Barish, who is the person who joined the experiment late. He only arrived on the scene in 1994. However, he is the visionary behind upgrading the sensitivity of the instrument to the level where this detection was possible. The original LIGO could not have made the detection, which was possible thanks to the development initiated by Barry Barish.
So the other two worked like for 50 years with this project. What did they say when they got the call from Stockholm this morning?
Well, I think they were expecting it, more or less. As I said at the press conference, the first discovery of a gravitational wave, the first direct measurement, caused a sensation worldwide. So it's been speculated already for a year that this was a deserving discovery. And so I think they were half expecting it. They were still humbled and very, very gratified that they were awarded the prize, but also all three of them mentioned, one, that they were happy that they were not alone, and two, that we should make sure to stress the role of the collaboration at the press conference and even at the award ceremony.
So how was this collaboration? The LIGO collaboration?
Yes, the LIGO collaboration has grown over the last 40 years. In the beginning it was small, it was just groups at MIT and at Caltech, at the universities in the United States. But then as the detector grew in size and people started talking of kilometer-long arms, the collaboration also grew, and groups joined all across the United States, but also in Europe. and in Australia. So today, the LIGO collaboration consists of scientists at 90 universities all across the world.
So you are like going to invite to Stockholm like 1,000 scientists?
Would like to. Unfortunately, I don't think it is possible, but each Nobel laureate has the opportunity of inviting a certain number of people, so I hope that we'll get representatives from across the collaboration.
So now when the gravitational waves are here, in some sense, what will they tell us about the universe?
So what we hope to learn from the gravitational waves is, one, about black holes and about gravity in its strong regime. You have to imagine gravity as the weakest force we know of. It's much weaker than electromagnetism. Just think of a kitchen magnet, a small magnet you put on the door of your fridge. It stays up, it doesn't fall to the ground, which just shows you that electromagnetism is much stronger than gravity. So the gravity forces we know of from the Earth are weak. Gravitational forces close to black holes are extremely strong. So the discovery of gravitational waves carrying information from the surroundings of black holes will teach us something about the strong regime of gravity, which is very, very exciting. We'll learn something about violent explosions, like supernovae or gamma ray bursts. We might learn something about the Big Bang, because the Big Bang left imprint on the universe in terms of gravitational waves, which we've never seen before. They're even weaker than those which have been observed previously. But even more exciting, there are parts of the universe which are dark, which we've never seen before, because electromagnetic radiation doesn't reach us from there. Gravitational waves are unstoppable, so they will. So we hope to learn about this dark universe.
Thank you very much, Olga Botner, for taking your time with us.
Thank you.